have a speed of 300 meters per second, calculate frequency. You are still coming from V, F, lambda. You are calculating for frequency, which is V over lambda. Our velocity is 300. Our wavelength is 0.52. We can divide straight away 300 divided by 0.52. Then we are going to have 576.9. 576.9 hertz. 576.9 hertz. Let's consider these questions as simple as it is, but somehow logical. The velocity of a sound wave at 27 degrees Celsius is 360 meters per second. Its velocity at 127 degrees Celsius is velocity of a sound V is directly proportional to the square root of temperature. The velocity of a sound is directly proportional to the square root of temperature. But what can we derive from that? This is equal to K, square root of what? Temperature. And this is V divided by square root of temperature is equal to what? K. And once we have something like this, then we can have V1 over square root of T1, V2 over square root of what? T2. This is what I'm going to use to solve this that question now. Okay? If we look at the equation, the velocity of a sound wave at 27 degrees Celsius, that's your T1. Let's take it. T1 is 27 degrees Celsius, which is plus 273. Okay? To have it in Kelvin. Okay? And if you have 273 plus 27, what are we going to have? That's 300 Kelvin. That's what we're having for T1. And we have for V1, which is 360 meters per second. If you look at the question says the velocity of a sound wave at this temperature is this, which is V1. Okay? The question now says its velocity, V2, we are not given. But we are given the T2, its velocity at 127 degrees Celsius. So, for our T2, let's look at this, which is 127 degrees Celsius plus 273 again, to convert this value to Kelvin scale. So what are we having? So let's quickly look at that. So if you have 127 plus 273, we are going to have 400 Kelvin. Then we are going to make use of this equation. V1, what is our V1? That's 360. What is our T1? That's 300, square root of 300, which is equal to, what is our V2? That's what we are looking for. What is our T2? Square root of 400. Cross multiply. V2 times square root of 300 is equal to 360 times square root of 400. Can you see that? So that V2 will be equal to 360 times square root of 400 divided by square root of 300. That's what we are having. Since you can use your mathematical instrument straight away, you can easily find what will be the value. This is V2 is equal to 360 times what will be the square root of 400. That's 20 straight away. It's a perfect square root. Then What will be the square root of 300? Okay, that one will not give us a perfect square. That one give us that 17.32. 17.32. Then from there you can multiply straight away. Okay, that's 360 times 20. We are going to have 7,200 divided by 1732, which is equal to 17.32. We are going to have 415.70. And what are we looking for? Velocity, meter per seconds. And that's the answer for that question. Let's consider this question. The question says, any line or section to an advancing wave in which all the particles are in the same phase is called A. Wavelength, B. Wave crest, C. Wave trough, D. Wave amplitude, E. Wave front. The answer there is wave front. Any line or section to an advancing wave in which all particles are in the same phase. Take note of the phrase, all particles are in the same phase. That is wave front. Wave trough. This is, let's say we have, this is a wave. This is the crest of a wave. This is the crest. This is the trough. Okay? This is the wavelength, the distance between two successive crests or two successive troughs. This is the wave amplitude, the maximum distance with the maximum displacement undergo by a particle is the what? The amplitude. Okay, so all those ones we are given doesn't have anything. So the best answer there is wave front. Wave front, whereby the particles are in the same phase in a wave motion. That is wave front. Question, another question says, the following types of wave are all transverse except A. Light waves, C. Radio waves, A. Light waves, B. Radio wave, C. Sound waves, D. Surface wave on water, and E. X-ray. Transverse wave, this is perpendicular. Longitudinal, they are parallel. Under this, the question now says, the following type of waves are all transverse, except radio wave is a transverse wave. The surface wave from water and light wave and X-ray, they are all transverse wave, which means transverse wave is electromagnetic, because all the following examples given here are also the examples of electromagnetic wave. An electromagnetic wave are the wave that does not require a material medium for their propagation. But if you look at sound wave is an example of a mechanical wave. Okay, so sound wave is not part of the example of transverse wave, and the right option there is option C. Another question says, which of the following types of wave cannot travel to a vacuum? Let me tell you this. Any wave that can travel in a vacuum is an electromagnetic wave. It's an electromagnetic wave. And what are the examples? Infrared wave, radio wave, X-rays, gamma rays, light waves. Those are the examples of waves that can travel in a vacuum. So now the question now says, which of the following type of wave? Before I go into that, any wave that can travel in a vacuum, that kind of wave do not require a material medium for its propagation or for its transmission. Okay? But a wave that needs a material medium, that is a mechanical wave. Okay? And the example of that is a sound wave, the wave on a rope or on a spring, water wave. Okay? The question now says, which of the following type of wave cannot travel to a vacuum? A. Sound wave. B. Light wave. C. Infrared wave. X-ray radiation, radio wave. If you look at all the options, only sound wave is an example of a mechanical wave. All the other ones are electromagnetic. So sound wave cannot travel in a vacuum because it requires a material medium for its propagation, and it is also an example of mechanical. Finally, we are going to consider this question. The question says, in a ripple tank experiment, a vibrating plate is used to generate ripples in the water. If the distance between